We now pick up for discussion two important forms of differential equations, and apart from their importance, I would say that they are more useful. They are very simple looking equations, but they are very useful in the sense that these types of equations occur in many physical problems. So one should know how to solve these equations, how to recognize them. It's very, very important. The first one is this, which is the first order, first degree equation. The form of this equation is dy dx plus py is equal to q, where actually p stands for a function of x and q stands for a function of x also. These may also be constants. So either one or both of them can also be constants. So dy dx plus py is equal to q, where it is understood that y is the dependent variable and x is the independent variable. I will write the same equation using two other symbols, but the form it does not change. Supposing we take ds dt plus p s is equal to q. Now here s is the dependent variable, t is the independent variable, p is a function of t, q is a function of t. So these two represent one and the same form. In fact, why I have written this is that in most physical problems, the variation of quantities with relation to time is what is needed. So that is why when this particular equation written down in y and x terms presents itself in physical problems, then y and x are replaced by other symbols, and this generally happens to be time, because the time variation of physical quantities in different problems is very, very important, and that's what we are looking for in various problems. Here there is a philosophy of solving this equation, and that is, we can see that on the left hand side, this is not the derivative of any product of two functions. Had it been y into p and this is some derivative of function, then we need some other term here to make this a derivative of a particular product. We'll do that by choosing something called an integrating factor. The purpose of an integrating factor is to render the left-hand side of the transformed equation as the derivative of the product of two functions. So what we will do is we will start by multiplying the whole equation by an unknown function, which we will try to get under certain assumptions, and then this equation can be solved. So what we are going to do is, let us use a little bit of Braun, shear force, and say that let us multiply both sides by some function Vx, and this has to be chosen appropriately. How appropriately? So that actually we are home. And we are home only when we can solve this equation for given values of P and Q as functions of X. I always say that, doing these kind of things is like playing football. The target is to do something so that the ball ultimately gets into the net of the opponent's goal. That's it. Not into the same side, into the opponent's goal. So, having said that, if we multiply by Vx and write only V for Vx, then we get V dy dx plus P V into Y is equal to Q V, where, as we said, V is actually Vx. So we reiterate that V is equal to a function of X. Now comes, how do we choose V so that it's to our advantage? We will take this equation on top, rub out this, and say or narrate the philosophy of choosing V. V This comes to our advantage if we choose the function V in such a way that PV is nothing but dV dx. Then the whole equation would look like V dy dx plus dV dx into Y is equal to Q into V. So we see that if we can make a choice of V such that PV is equal to dV dx, then the left hand side actually becomes the ddx of Y into V. V dy dx plus Y dV dx. This becomes nothing but the ddx of YV. And that can be written as QV. So we will see now the equation is transformed to the ddx of YV is QV. In other words, Y into V is equal to QV integrated with respect to X. That's fair enough, and that's perfectly all right. So now we will focus on what this means, choosing dV dx as equal to PV. What does that mean and what value of V is it going to throw out? If we just write down dV dx is PV, then this implies that dV over V is equal to P dx. In other words, integral dV by V is equal to integral P dx. Now dV by V is nothing but log E V, and that is equal to integral P dx. In other words, this implies that my function V that I am looking for is nothing but e to the power of integral p dx. That's it. So this is the v that emerges, and this v, when multiplied into the original equation dy dx plus py is equal to q without the v, will transform it into an easily solvable equation. So ultimately what will happen is the equation will transform as follows. So one can write choosing v as e to the power of integral p dx leads to a new equation that looks like d dx of y into e to the power of integral p dx is equal to u v. In other words, this implies that y e to the power of integral p dx is nothing but integral u v dx. And of course, at the end we put a constant. This part is a bit theoretical, but we'll take a simple example and then we will see the whole process working. That means one can see the process sort of playing. So we'll do that now. We'll select an example and try to solve it. Let us take an example in which we write dy dx plus y tan x is equal to sec of x. So here we have dy dx plus py is equal to q. So we can identify tan x as being p in the standard form and sec x being equal to the q of the standard form. Dy dx plus py is equal to q. Now we just saw that to transform this equation in such a way that the left hand side becomes the d dx of y into something, we have to multiply by an integrating factor. That e to the power of integral p dx is called the integrating factor. So here we write the integrating factor as e to the power of integral p dx. In other words, that is e to the power of integral tan x dx. All of us know from class 12 integration that tan x will integrate to log sec x. So this is e to the power of log sec x, and that is by the rule of e to the power of x log a. This is nothing but sec x. So our integrating factor in this particular case is sec x. We will now multiply the original equation by sec x, and we'll remove this work from here because we found the integrating factor to be sec x. We will just keep it in mind and multiply by the integrating factor. So one writes multiplying by sec x, we get sec x dy dx plus y into tan x sec x is equal to sec square x. Now one can easily see that the left hand side is now transformed into the d dx of y sec x, because it is first function derivative of the second plus second function derivative of sec x, which is nothing but sec x tan x. So this means that we now have the d dx of y sec x equal to sec square x. When we integrate this, we will get y sec x as tan x plus c. So we do that a little on top. Integrating leads to y sec x is integral of sec square x dx, that is nothing but tan x plus c. So our solution is y is equal to tan x divided by sec x plus c divided by sec x is c cos x. C divided by sec x is c cos x, and tan x divided by sec x, one can see, will be sin x. So this is equal to nothing but sin x plus c cos x. So this is our y as the solution of the differential equation. Now we'll do one thing extra, and that is to see whether if one started with this family of curves y is equal to sin x plus c cos x, one could arrive at the differential equation we just solved to arrive at this solution. So we'll do that exercise. So the question now changes a bit in the sense that we will check out whether this particular solution, so let's write to check whether this solution leads to the equation from which we got it. That's very important. If we can show that, then we are again, in my language, we are home, because it stands to reason to believe that if this is the solution that is thrown out from the given equation, then this solution must satisfy the original differential equation. So we will draw out everything from the board and take this and create a differential equation from that and see what happens. Y is sin x plus c cos x. Differentiate once. dy dx is equal to cos x minus c sin x. What we'll do is, we'll write these equations in a different way. This implies that y minus sin x is equal to c cos x, and c sin x is cos x minus dy dx. That's fine. If dy dx is cos x minus c sin x, then c sin x is equal to cos x minus dy dx. Purposely written with the c's on the same side so that now we can divide one term by the other and c will get eliminated. So two of them together tell us y minus sin x divided by cos x minus y1, y sub 1 is dy dx, is equal to c and c cancel, cos x by sin x is cot x. We then write, this implies y minus sin x over cot x is equal to cos of x minus y1. y1 is dy dx. Now, y over cot x is y tan x. Minus sin x over cot x is cos by sin, is minus sin square over cos, so minus tan cos. Okay, sin by cot, let's see. Sin x by cot x is equal to we can write tan x sin x. That's simple actually. We could have done this straight away. 1 by cot is tan x. So minus tan x sin x is equal to cot x minus y1. So y1 plus y cot x, y tan x is equal to cot x plus tan x sec x. We'll take this up and write it on top. This can be rubbed out now. We'll write y1 plus y tan x is equal to y1 plus y tan x is equal to cot x plus tan x sec x. Now we will see whether the solution we just got, that means y is equal to sin x plus c cos x, will lead to a differential equation which is exactly the one from which we started to get this particular solution. So we've written down the solution, and now we are going to find out the differential equation of which this is a solution from here. So this is the given data. In other words, we can reformulate the problem. If y is equal to sin x plus c cos x represents a single parameter family of curves, because there is only one constant. So this represents a single parameter family of curves. Find the differential equation from here. The process is very simple. I have already done the board work. y1, the first step is y1 is first derivative cos x minus c sin x, or c sin x is equal to cos x minus y1, just a rearrangement of terms. And we also have the original solution, that means c cos x is equal to y minus sin x. These two equations, one is the equation written in a different form, and the other is a derivative of the first equation. If we just divide these two equations, divide the first by the second, on the left hand side c and c will cancel, giving us tan x, and on the right hand side we have cos x minus y1. y1 represents the first derivative, and y minus sin x is the denominator. This implies y tan x minus sin x tan x, this is here, is cos x minus y1. Now upon transposition of terms, if we get the y1 on this side, y1 plus y tan x is nothing but this cos x plus sin x tan x. And this is a very simple trigonometric simplification, because cos x is cos x and sin x tan x is sin square x by cos x. If we multiply these two, cos square x plus sin square x is 1, and then cos x is the denominator, we get sec x. So we do get indeed that y1 plus y tan x is equal to sec x. That is the required differential equation. So we see it works both ways. That means if we start with a particular differential equation and get to a solution, that solution must satisfy the differential equation from where we started.